So recall that last time I was talking about what are normal subgroups. We'll continue on that, and today I will now talk about some more basic properties of normal subgroups. So remember, H is normal in a group G if XH and HX coincides for every X in G. And we saw, for example, that center of any group is always a normal subgroup. And secondly, we saw any subgroup of a group of an abelian group is normal. Normal if H is abelian. Now you may also try to think about the converse of this statement. That is, uh, if for every subgroup H of G, H is normal in G, then whether you can say that G is abelian or cyclic or whatever. You can also try to think, or maybe you can also try to find some counter example of a group where each subgroup is normal, but the group is not, say, cyclic or more generally more non-abelian. So let's see. So today we will talk about some applications of these things. So firstly, suppose you have a situation that. So even before that, let me define no, define what is a quotient group. Then it will make more sense to talk about these things, these applications. So yeah, so suppose you have a group of it may be finite or infinite, you have a non-trivial group, and you have its normal subgroup, let's say H. Then I'm taking all the distinct left cosets of X of H in G, and I'm denoting this set by G modulo H. And now I'm giving it a binary operation on this set. So far we just have a set, and I'm defining a binary operation. So you take two elements of that set. It will look like xh and yh for some xy in G, and I'm sending it to xyh. So now say if xh and x1h are same and yh and y1h are same. What can you say about these two elements? So let's see. So remember, this is elements of this form, right? And so if you say that both of them are same, that is same as saying that uh, x1 y1 inverse xy is in H, right? That is the property of left cosets we have seen before. This is same as y1 inverse x1 inverse x y, that is in H. Now let's see if we can do it. And because we have these two are same, so this means x1 inverse x is in H, and also y1 inverse y is in H. That is what we have so far. So now uh, let's see. So we start with this element. We take this element and we'll try to use uh, these two relations. So let's see. So now this thing belongs to H, right? Because of this. So we have y1 inverse hy. And now remember H is a normal subgroup. So we have so far not used this normality of H. So now because H is normal, this right coset will coincide with this corresponding left coset, and also this thing is now in H. So this means this coset will coincide with the uh, group H itself. So we get this belongs to H, meaning that this relation holds, and this means if I define this star, so star is well defined. So and also if you take this coset corresponding to the identity element, this will go to YH for every Y in G. So we get that this, or you can write it as simply H, is identity element. And lastly, if you take three such elements, then you can show that. So this is by definition you get ABH and then CH, which is then ABC of H. And if you just, or maybe you can write it as first you are taking AB and then C. So you can think it like this as well. Yeah. And but now this is same as BCH and this is ABCH. But remember G was a group, so by associativity you can say this element is same as this element, which means these two cosets are same. So we indeed get G mod H with this binary operation becomes a group. And if G is a finite group, then this group has how many elements? This is precisely the number of left cosets of H in G, or the index of uh, H in G. So yeah, so the useful thing to use, like the useful thing with quotient groups is that suppose you have a group with a finite group, but the order is too large to compute or too large to handle with. So if you can find a normal subgroup and then you take the quotient group, you may also try to just decrease the order of that group, right? Because once you take the quotient group, the order will you just like uh, you can take the order as order of G by order of H, right? So if order of G is finite but very large, then you may try to find a normal subgroup H, and then if you take order of G by order of H, you will get the order of the quotient group, and this order will be less than order of G. So yeah, so that is one useful thing to useful thing about quotient groups. So yeah, so now I can talk about those applications. So let's see. Maybe for example, one group we have already seen that if you take G to be the cyclic group infinite Z and H to be say generated by any element nz, then this quotient we have seen already that this is just Z mod nz. This is a cyclic group of order n. Yeah. So whenever you have a normal subgroup, you can talk about the quotient. So now we can talk about the application. So suppose you have a situation that center is a normal subgroup, so it makes sense to talk about this quotient. So suppose this quotient group is cyclic, then my claim is then G is abelian. Yeah, it's not very difficult. Just like to show G is abelian, you just need that for any two element in G to show that AB and BA both are same. Now you may take the A bar and B bar inside this quotient group, and because this quotient group is cyclic, so let's fix the generator, say X bar. So then A bar will be X bar power n1 and B bar will be X bar power n2. So it means A is X bar n1 times some element of the center. Let's call it A prime, and B is X bar n2 times some element of center. Yeah. And now it's really easy because if you take AB and you take A inverse B inverse, you just get X bar n1 A prime X bar n2 B prime. Then A inverse will be A prime inverse minus n1 B prime inverse X bar minus n2. And now remember, because A prime and B prime are coming from the center, these elements always commute. So you can just take these two and then you can further switch these two elements. So you will get X bar n1 n2 n1 plus n2 with B prime A prime A prime inverse B prime inverse. These two will cancel. These two will cancel after. And lastly, you get these two will cancel. So you get 1, which means that so this is this. So we get AB and BA are same. So we get indeed that G is abelian. So again, from this application, the useful thing is that, say, suppose we let say order of G is say for example 91. So then what can you say about the order of its center? So first thing is 91 is what? 91 is 7 times 13, right? So the possibility for center is either 1 or 7 or 13 or 91, right? Because order of the center divides the order of the group. But if it is 7, then the quotient group would have order 13, right? So it means that this is cyclic because the order is a prime number. But this means G is abelian by this application. And this means order of G is order of the center, which is 91. But that is false because we have assumed that order of the center is say 7. So that is false. So this cannot occur. Similarly, uh, order of the center cannot be 13 because then you can replace everything by 7. So either it is 1 or it is 91. So if you are given that the group is non-abelian, then you know certainly that order of the center cannot be entire G. So in this case, you get G is abelian. So from this application, you can directly say that any non-abelian group of order 91 must have trivial center. There is nothing in between. Either it is full G or it is just this means this is just identity. So that is a nice application. Maybe you can also, like, there is nothing special about 91, right? You can always take, say, order of G is PQ, where PQ are distinct primes. So similar argument will also hold for this. So yeah. Now the second application. So suppose you have a group G and you have two subgroups such that one of them is normal. Let's say H is normal. Then you take this set HK, that is all possible elements H from H and K from K. I'm defining the set HK to be like this. So this becomes a subgroup. Uh, so if one of them is normal, uh, then that would imply that HK is a subgroup. So let's see. So what you need, you take two elements, this and this. So you show that this is in HK. So we get like this. And now we will use the property that H is a normal subgroup. So H is normal means G H G inverse is G for all G in G, or you can write it like this. So we'll try to use this property. So we somehow need to rearrange this element to write something like some elements from H and times some element from K, right? That is what you need to show in order to show that H is a subgroup. So what we will do is, let's see how we can do it. So we have like this. Then you first keep H1 as it is. Then you take, say, or maybe I can do it in this way if this is complicated. Uh, let's see if we can do it in this way also. So yeah, or maybe we can do it in two steps. First, let me take this and this. So this you can write it as K1 H2 K1 inverse. But yeah, again, because this is H is normal, this element must belong to H. So we get this is an element of H. This is also an element of H. So product of two elements of H will give you another elements of H. Let's call it H3. And these two are in K, so their product will be in K. Let's call it K3. So we get this is an HK. And secondly, if you take any element HK and you take its inverse, you get something like this. And now, how do you show this is an HK? So again, you just use the normality of H to say this is K inverse, right? I can write it like this. But again, because H is normal, this element belongs to H, and this element is K. So this is some H prime K prime. So we get HK becomes a subgroup of G. So we need at least one of them to be normal. Now the one thing you can take it as a question that if H and K are two subgroups, none of them is normal, find an example that HK is not a subgroup of G. You can try to find an example such like this. So yeah, and next time we'll talk some more properties of normal subgroups. We will try to figure out what is order of this set in case H and K are finite, and then we'll move on to group homomorphisms and more things.